Swayam Prabha. Digital India. Educated India.
So I will not really go in detail about my introduction, but I have been here past 15 years now. I joined 2010. Before that I was working in industry, Slumberger, again oil and gas industry. So my major domain is working in oil and gas industry, and I still love oil and gas. So, but then of course we have to understand that CO2 is a problem. So then I started looking at CO2 aspects as well, and being a chemical engineer, and I find that there is lot that we can do to capture carbon dioxide and sequester it. And I will also show you the discussion over a period of time that how it is important right now. Anyway, so at IIT Madras, our research group is working on various aspects. One is of course carbon dioxide capture and sequestration in onshore and offshore, both in hydrate form also where we are looking at it. We have also worked on carbon dioxide sequestration subsurface in depleted oil and gas reservoir for enhancing oil recovery, so that you can recover oil out of it. And we have been again working on different aspects of drilling fluid, fracturing fluid that she was talking about. We have been working on flow assurance, and we have been working on also nanoparticle applications for improving the performance of, including carbon capture, sequestration, gas hydrate, flow assurance. So we have been using nanoparticles for many of these applications, and during next couple of weeks you may get a chance to understand some of these aspects. So today's talk is primarily, I will focus on properties of carbon dioxide, and then mainly on capture side, CO2 capture and transportation. And of course, as I said, that there will be a talk given by various other faculties which will cover utilization, catalysis partly, maybe conversion, maybe electrochemistry, etc. So we will have to figure it out. You have to connect the dots, right? So anyway, so she has already discussed about these climate issues and how the temperature is increasing. We have been closely around 420 ppm or so, and then we have been releasing about 36 gigatons of carbon dioxide into the atmosphere every year, and it is increasing day by day, right? Why it is important? Even if you talk about 420 ppm, the question is that whether it is really matter of worry. It's like out of 1 million balls, we have 420 balls, alright. So do I really worry about it? It is indeed. There have been certain lab scale experiments where it has been shown that small amount of CO2 can be responsible to generate or increase the temperature. If you really make sure that all the conditions mimic the atmosphere, then the temperature will rise. For example, I sit in a car, I just close the door and then come back after a while, you can feel that car is hot, you cannot really stay inside, right? So this is a greenhouse gas effect, then we have to really worry about it. And of course, if you look at the data past several years, there is a rise in temperature. It is of course because of CO2, and of course there are various other factors that also includes, but then one factor is carbon dioxide emission, right? Now how can we go for net zero? Of course renewables is something that we have to worry about it. But can we really go for renewables? That is a question. Can we really take care of my all energy requirement from wind, solar or so, right? No, it's not possible, because today our energy mix is about 82% energy mix is coming from fossil fuels all over the world, right? Looking at the growing economy like India and China, we are primarily being dependent upon fossil fuel, including coal, oil, gas, right? If you go out of the campus, you will find several thousands of cars, automobiles running, including two-wheelers, and you will find that all use oil, petrol. If there is a bunk, strike by petrol pump, I think there will be a mess in city, right? All prices will go up, right? So energy is very important for our living. If you know that if you do not get oil, there will be energy crisis. And if energy crisis is there, then there will be a food crisis. So all this is connected, right? There is nowadays, it's not that we get only a locally made food available. We cannot survive on one thing, right? So energy is very important for our living, right? And our energy requirement is increasing day by day. I joined in 2010 in IIT Madras campus, and I see that there were very less cars, even as assistant professor when I joined, I did not have a car. I got it in 20, 24, 21 or 22. I was happy riding my cycle. It's okay, I am living in a campus, why should I need it, right? My children were studying in Kendriya Vidyalaya, so okay, they were going in two-wheelers, so I did not have a car, to be honest. It is not that I was not able to buy it. But today, any assistant professor who joins in the campus comes with the not two cars, not only one car. Because his wife is also working, he is also working, so both of them have a car. So you can change this, you can see the difference, right? All the classrooms are becoming air conditioned, right? Now that energy is not coming from somewhere, it's coming from electricity, and electricity is ultimately coming from fossil fuel, right? So we have to understand that our energy requirement is increasing. Just looking at everything, that I have a dishwasher, I have all kind of equipments, electric equipments, and that requires energy. So energy is very important, right? So in a short time, or at least 3 to 4 decades, I do not see that we are going away from fossil fuels, right? It's not going to happen a magic that suddenly after 2 years we will have something that completely coming from renewable energies, right? And there have been again certain studies which shows that even for 50 to 60 years fossil fuel will dominate the energy basket. So the international energy agencies says that. Anyway, I am not really going in detail about that. So what is that? Pollution we talk about, man-made pollution. We have a solid land pollution, everybody is aware of this, right? We have a liquid water that pollutes our rivers and everything, and you have air pollution. 3 major form of pollution. Now what is the difference between that? If I go back and see, I can easily segregate this solid material from the lands. I have plastics, I can segregate that easily, even I can hand pick that. It's easy for me to separate out from the land, right? Go with the water, liquid phase, molecules are different. It's slightly challenging for me to separate dyes into the water. So I need a membrane, RO, reverse osmosis, and all kind of chemical processes that requires additional energy, right? Go for air pollution, very difficult. Once it is in air, you cannot really, I cannot say that you see the CO2 molecule is going from your nose, you capture that and put it in the dustbin. I cannot say that, right? So a molecule that goes into the air, it's difficult to capture, right? So either you have to segregate before you make the pollution, or you segregate after you make the pollution, which is easy for air. Before, right? So you segregate it before you release into the atmosphere, right? That is the more challenging aspects of air pollution that we talk about. Of course, air pollution requires other particulate matter and many other stuff that I am not really going in detail. But as CO2 is concerned, we have to ensure that there has to be technologies which should be developed, so that before they go into the atmosphere, we should capture that and dump it somewhere. All right. Now, of course, now this CO2 emission is increasing, and as I said, that majority of this energy consumption is responsible, like transportation, energy used in building, other industries, etc. And of course, there are agriculture, forestry, and other industries. So energy is a major section that results in a pollution of CO2, carbon dioxide. Anything, you have a flyover that you can see in Adhar, right? They are building a flyover everywhere, right? Ultimately, that results in pollution, because you have to generate a cement, steel, and everything. You have cranes running there, everything, right? So to generate a cement, you require lot of energy. You release CO2, etc. Even you generate a steel, that is required there, right? So every activity, every man-made activity ultimately has a CO2 footprint. Even the chair that you are sitting in is not a net non-CO2 free, right? It has generated certain amount of CO2 into the atmosphere. So why I am telling is that we are talking about today $3 trillion economy. Prime Minister says that we have to go $10 trillion, $5 trillion, and so on and so forth. Every country wants that, right? Can that come saying that I am not going to emit CO2 and still I have a $10 trillion economy? It's not possible. There have been certain correlation of CO2 emission with economics rather than really population, right? The more you want to be your economy higher, you become more consumer. You consume and throw, right? So the sustainability is an important aspects of this whole game. Anyway, going forward, now the global temperature is rising. I think Madam had already covered that. Land to global land to ocean temperature anomaly, and it is over somewhere about 1970s, 80s. It is beyond that. It is increasing. Now there are various scenarios that shows that if I capture carbon dioxide, if you do not capture carbon dioxide, or so how the temperature annual mean global temperature will rise in next few years, right? And there are certain models. I think Madam will cover in detail about that, so I am not really going to spend more time on that. But you have to understand that we have to predict the future 20, 30, 40 years down the line in both energy, environment and earth. So if you look at the name of my lab at IIT Madras, I have written at 3E lab. It talks about earth, energy and environment. It is a nexus. I cannot say that I do not want energy, but I want less CO2. The more you want energy, you are going to release CO2 into the atmosphere. So you have to dump that into the earth, or you have to take care of your environment, right? So all these 3 E's are important when you look at overall climate change, right? So all these nexus has to be understood. Anyway, so this is an example of coal, right? In 1970s, 50s, 40s, you might have seen the steam based, transportation through trains, etc. British were used to have trains, right? And then because of pollution, they stopped that. I am not going to run on the train because it generates a lot of pollution. I should run it on electricity. Now, most of the trains are actually running on electricity. And this is the data that shows, somewhere in 1950 onwards, the use of coal in transportation has decreased. It's almost negligible now in 1990s, beyond that, right? I do not see coal. Earlier, where I was a child, I can go into the market, buy a coal, right? Coal was even used in household, right, for cooking purpose. Kerosene was used in household, right? But today I go into the market, I will not get a coal easily. I have to find out, somebody will say that you go here and there, right? Getting coal is not an easy right now in the general market, right? But look at the coal uses in the electricity generation. It has increased. So when we cannot see something, does it mean that we are going away from the coal? No. Today also, as Madam said, that Germany wants to go again restart their coal fired power plant. I was reading couple of weeks back, New Zealand also wants that, they want to import fossil fuels, right? So they have realized that it's not quick decision to say that I am not going to use fossil fuels, right? So even if electricity vehicle, for example, I am little critical about electricity vehicle, not because they are very clean, of course they are very clean, but they looks like clean, but if you go back and look at your calculations, you will find that they are more difficult for environment, because they are not going to improve the electricity requirement. Where the electricity will come from? If we really want to generate all electricity coming from solar energy, then that's fine, right? But I am not seeing that to happen anytime soon, right? Even to generate silicon solar cells, there are calculations in the literature which shows that they also generate CO2. So nothing is CO2 free, net neutral. So less than 1% of electricity vehicles are there on the road. There are about 15 million or something electricity vehicles are there. Less than 1% are right now electricity vehicles, right? But given the fact that, okay, I am happy with the electricity vehicle, does it mean that from this that I am going to go away from fossil fuel? I require more energy. Anyway, going forward, so CO2 in the atmosphere. So nature has its own way to address the CO2 concern. It has said that, okay, whatever CO2 is being emitted, I will capture that. So 50% of CO2, almost 50%, it has been said that nature takes care of it on its own, it absorbs. But because we are growing our economy and we are burning more fossil fuels, the net CO2 that is going into the atmosphere is increasing gradually in a year, and it is getting accumulated. So this is what a schematic shows, that plant life, soils and atmosphere, they capture and also release. So there is a continuous exchange of CO2. There is a continuous exchange of CO2 from the ocean, right? And because of human activity, the net CO2 that goes into the atmosphere is there, right? So this is what it is, this is some numbers, gigatons. So it says that nature emits certain amount of CO2 So he says that nature emits far more than us. You see, I am only emitting 33 gigatons, right? 34. But he said, look behind you. He said, nature is also taking care of it. Ultimately, most of the CO2 back into the ocean or lands or plantation, etc. So this is a net emission that is happening into the atmosphere, which results in increase in temperature, right? Now the question is that how can I take this one, right? Address that. I already told that it's a very challenging. It's not an easy, and that's where it is very important to develop technologies which can address this. Now this is a CCUS supply chain. So it is not that I just want to capture it, carbon dioxide. What do I do with the CO2? If I give you a 1 ton of CO2, I said you take it to your home. What do we do? What you will do? You cannot do anything, right? You cannot eat it. You cannot do this anything. Plant has a natural way of absorbing CO2, so I cannot do that. So people has to look at whether I can convert that carbon dioxide into some hydrocarbons or some value added products, or I can dump it somewhere below the ground, right? But as I said, CO2 is a liquid, CO2 is a gas. So I have to capture carbon dioxide and then transfer that through pipelines. So I have to process that and then liquefy. So I have to capture the CO2 from the power plant. Then you have to develop a facilities, and then you transfer that through pipeline below the underground. To transfer that, you have to have a CO2 injection wells that madam will discuss over a period of time, right? And then you can also transfer that into the ocean, subsurface sequestration in the ocean. So you can dump that into the onshore, below the ground, or offshore in the ocean. Now in one of my talk next week, I will discuss that how oceans are very ideal candidate to sequester carbon dioxide. Scientifically, it is very attractive, Anyway, so when you talk about onshore or offshore, you required all these facilities. You required processing, liquefaction, pipeline, and then ships, and then you have to sequester below the ground, onshore or offshore in the ocean. Now this is a CCS supply chain: carbon dioxide capture, transportation and sequestration, and utilization, where you have to convert that into value added product like methanol, like ethanol, or what else, dimethyl ether or something like that. What kind of product that you can convert CO2? Anybody else? Urea. What else? Carbonates, methanol, right? If you understand that most of these conversion process still requires energy, right? The raw material that you required, for example methanol or any other stuff, required some kind of hydrogen molecule. Where the hydrogen will come from? Today 99% of our hydrogen comes from fossil fuel, right? Less than 1% comes from so called green way, less than 1%. This is International Energy Association report says that 2021, right? So conversion is still a long way to go. Utilization, unless I could get hydrogen from biomass or something from water by splitting water through solar energy, which is again very tricky, So of course there are technologies available, but these are not something that can be looked at large scale. I cannot generate and say that I have all hydrogen coming from solar power plants, by splitting water. I can do that experiments in the lab, but no, still it's long way to go. So what is a quick way to act? I am not criticizing any technology right here. I am saying that I do not have a time, I want some certain quick decision. So quick decision is that I have to dump it somewhere. Huh? Dump it in sea or onshore? No, I will tell you that it's not that. It's at least more favorable in ocean or in onshore. Scientifically, it is proven that, right? So anyway, we will discuss that. Now these are various pathways which have been there under development. We have CO2 that can go into generation of biofuels, algae biomass. You can do that. So you can capture carbon dioxide from the power plants. Additionally, you can store that into the permafrost, into a region where the temperatures are much lower, like Siberia, Russia, northern and this part. You can store that into the depleted coal fields for coal bed methane. So you can also generate methane out of it and you can sequester carbon dioxide into the coal fields, right. You can also have a geological sequestration in aquifers, saline aquifers, or you can also have in a depleted oil and gas field. Depleted oil and gas field is something which is very promising candidate, because we have been producing oil and gas for several years and we know the geophysics of these oil fields very well. As an engineer, I have learned geophysics. Some of you should learn, it is very interesting physics, so there is a cap rock and everything, So one may say that they may leak, but certainly you have to understand the geophysics before we dump this CO2 into the onshore depleted oil and gas field. The other potential region is the sea floor, where you can sequester that in the form of solid hydrates or below the seabed, and that I will discuss it in one of the next class, not the focus of today's discussion. Madam will partly cover this aquifers and EOR and etc. So though we have worked on that, but I think Madam will be best to discuss all these details. Anyway, so this is the ocean storage. So in ocean you can sequester in different aspects. You can do a CO2 plume sinking. You can have a disposal of CO2 in the form of carbonates, because CO2 can convert into the carbonates. You can actually have a CO2 liquid pools into the offshore conditions. Liquid pools, CO2 will form a liquid conditions in those conditions. I will discuss that in detail in next class when I teach that. So how the CO2 can form a liquid in the ocean and why it is safe, I will discuss that, And anyway, so this is what it is, a generally CO2 storage mechanism. You can have a flue gas, CO2 separated reactor, you have captured carbon dioxide compressed, and then you can transport that through pipeline or ships or risers, etc. Now there are various technologies which have been available right now, starting from CO2 capture to sequestration, right. And this is a TRL, technology readiness level, which starts from from concept to about commercialization. And most of the technologies, you can see TRL line 9, post combustion capture of CO2 from power plant, pre-combustion capture of carbon dioxide specifically from natural gas processing, transportation on onshore and offshore pipeline. So CO2 is being transported, even though in India we are not doing it, but in certain countries like Norway, for example, US, for example, there are pipelines available onshore, offshore, they are transporting carbon dioxide, right. Then transportation by ships, CO2 sequestration in saline formation, and CO2 injection in depleted oil and gas field, or for enhanced oil recovery. So these are all in TRL 9. There are certain technologies like CO2 storage is moved to proof of concept, and it has now also gone to the pilot scale. So it is now in TRL 6. Norway is doing that. So this is somewhere in TRL 6. This is an old slide, 2018 data that I have taken. And oxy fuel combustion, pre-combustion low temperature separation, biomass based carbon capture power plant. This is based on ionic liquids, and this is a membrane based separation, CO2 separation. So you can see that there are variety of different technologies which are beyond TRL 6, starting from pilot plant to commercial, most of them, and new technologies are also being looked at it. For example, one of my students, Prerna, is working on metal organic framework for carbon dioxide capture. So she will discuss that briefly in one of the discussion that we will have a separate discussion. So you can see that people are aggressively looking at starting from capture to sequestration. Different technologies are being looked at it, so that we can actually get rid of carbon dioxide. Anyway, so why this major focus on CO2 capture? Because anything that you want to segregate from air or flue gas is to capture carbon dioxide first. So there is one way that you can capture CO2 from flue gas, or another way is to capture CO2 from air. As I said, like 420 ppm, very small amount, very difficult. I do not know where the CO2 is lying here in the room. Challenging task. So that is called as direct air capture, DAC. People are also looking at direct air capture technologies. There are plants available commercially, but still they are not really being looked at in a major expansion. But slowly it is expanding because government has to do that. Now this is a junk that we produce. So it is not something that you have to see that I am segregating my waste. So I am not generating anything out of it, right? So I have to pay still to the corporation. I pay some money, they charge me a tax or something like that, right? So we pay for segregation. So similarly, as a human being, in order to ensure that we are actually in a safe environment, we have to pay for that. So there will be a penalty that will come in terms of money, right? Technologies are looking at how to reduce this cost of capture and transportation and sequestration. So in last few years, that cost has also slightly come down, looking at development in technologies, right? So we'll discuss little bit of that cost aspects, right? Now the CO2 capture, either looking at a stationary plant or point of source like coal fired power plant, or you can do that from direct air capture. You can convert that CO2 as a feedstock for petrochemicals and hydrocarbons. Again, challenging, as I said, it takes time. You have to transport that from the power source to the storage sites, either onshore or offshore by pipelines, and you have to inject that into the underground for enhanced oil recovery or depleted oil and gas field, etc., or you can do that in ocean, right? CO2 capture is traditionally done in natural gas processing and other industrial application. Earlier, it's been there. It's not that something started recently. Natural gas industry has been doing it since long time, right? But they were not focused about climate issues. So the technologies were available for specific application. Now the similar technologies are being expanded, and of course new technologies are also being coming up to take care of the CO2 from flue gases, power plant and other industrial activities where CO2 can be captured and stored. Now this is required significant strategic decisions. Why? Because one has to understand that you require to develop a CCS corridors where I can capture CO2, transfer that to the pipeline, sequester into the formations, or use this into the industrial applications. So CCS corridors has to be developed by different countries so that this overall process can be made very efficient, right? So anyway, what is important about carbon dioxide? Now if you look at this carbon dioxide phase diagram, everybody understands the phase diagram, right? Simple stuff. So you look at this, carbon dioxide remains gas in this zone, this is a liquid and this is a supercritical fluid. Now the temperature is about 300 degree Kelvin, which is the critical temperature, and about 100 bar, which is about 1500 psi or 100 atmosphere, right, or 10 megapascal is something that is the critical pressure for carbon dioxide. Any pressure 1000 psi, any pressure above than that, any temperature above than that, it becomes supercritical. Why it is important? Because we should talk about the onshore underground storage. Most of the temperature in the reservoir falls in this zone. So CO2 once it goes into the reservoir underground onshore, it becomes supercritical. Supercritical CO2 has a different properties. It's not the same property as like a gas. So you have to understand in that aspect. So what supercritical CO2 will have interaction with different reservoirs like sandstone, shale, etc., or basalt formation, etc. If you look at a CO2 into the ocean, if I want to inject that into the ocean, the CO2 at certain depth will become a liquid. Ocean temperature is somewhere about this condition, 270, close to 4 degrees centigrade, 270 to 80 degrees centigrade, and the pressure beyond certain point, 5 megapascal and beyond, it becomes a liquid, right? So if I want to dump CO2 into the ocean, it becomes liquid at those conditions. Anyway, we will discuss that in detail later on, right? But this is very important figure which tells you a different properties of gas or phases like gas, liquid and supercritical fluid as far as CO2 is concerned. Now everybody knows that any gas is ideal at normal temperature and pressure condition, Z is equal to 1, right? But as far as CO2 is concerned in the atmosphere, I do not have to worry about it. But when I want to transfer that through pipeline, either onshore or offshore, the pressure and temperature conditions will not be atmospheric condition, it will change, and therefore CO2 will not be ideal gas, it will become a real gas. Now how it looks like that, this is what it is, a simple schematic. This is a jet versus atmosphere. with respect to pressure starting from 0 to 1000. Now you can see nitrogen, you can see this is for hydrogen, this is for CO2, the extreme lower line is for CO2 and extreme second one is for methane. You can look at the Z for these 4 gases, they vary differently. Hydrogen, all are actually having a Z as 1 at normal condition of pressure and temperature, but as pressure increases, the value of Z differs for individual gases. For hydrogen, the Z always become more than 1 as pressure increases beyond atmospheric condition. So Z always increases beyond 1, and therefore you know that hydrogen storage is still a challenging task because of this property of hydrogen. Z is always more than 1. So amount of volume that is required to store hydrogen increases as you increase the pressure. So it has not become economical as far as hydrogen storage is concerned. Hydrogen has a molecular weight of 2, a very small molecule. So even if I say that I have a very tight proof container to store hydrogen, it will find its way to leak from anywhere. You cannot really control leakage of hydrogen so easily, unlike other gases, right? So hydrogen storage and transportation through pipeline is still very challenging. So hydrogen is not new to the mankind as energy, but because of these challenges, it has not come at a commercial level where I am going to use hydrogen in my house or hydrogen in a car. There are fuel cell cars etc. available, but still they are long way to go on the road, and that's the reality. So there are challenges available, and I do not see that challenges can be overcome in a short time of near future. However, look at the carbon dioxide. The Z decreases as the pressure increases and it goes to about 500 atmosphere, and beyond that Z continues to rise. Z less than 1 represent a slightly compressible behavior of the gas. So hydrogen is incompressible, you cannot compress that, but nitrogen do slightly, methane is better than that, CO2 is much better than that. CO2, if you look at this comes to about 50 bar, 50 bar is a pressure, minimum pressure, where Z is minimum. Then beyond 50 bar, as you go increase the pressure, the amount of volume required also increases to store that. So if I go and buy a cylinder of CO2 from a vendor, he gives me a CO2 cylinder at about 50 bar pressure, because that is optimum volume at which he can store maximum amount of CO2, right? For methane, this comes to about 200 atmosphere, you can see that. So you might have a CNG kit in your car, right? CNG, compressed natural gas. You go and fill this CNG, they will fill it about 180 bar to 200 bar, something around that. That is the pressure that they fill in, right? So that is the optimum volume or pressure that you can expect, to maximize your molecular storage in a given volume, right? So this is very important condition that tells you that about 50 bar condition pressure at atmospheric condition, atmospheric temperature, I can store maximum amount of carbon dioxide. That also gives me an idea that Z is very important to define the storage and transportation facilities by ships. For example, I will tell in one of the slides that CO2 is transported about minus 30 degrees centigrade in liquid form. So what is the pressure that is required in that condition? It can be low pressure, so I can have a container. LNG, you might have heard, liquefied natural gas, they transport it about minus 170 degrees centigrade at atmospheric condition, because methane becomes liquid at that condition, right? So similarly, CO2 becomes liquid at minus 30 degrees centigrade and atmospheric condition, so they transport that. It has been found that CO2 transportation by ships is more reasonable at those conditions, right? So some of these properties of CO2 are very vital to understand. Now look at this flue gas composition. This is exactly flue gas composition from SEPCOP, one power plant near Chennai, and they have a coal based power plant, and look at the amount of various components are there in the flue gas. You have ash, moisture, oxygen, nitrogen, argon. You have a SO2 that goes into the chimney, out of the chimney. Your sulfur trioxide, which is negligible. Carbon dioxide is 18%. 18%. Now one chimney, you can see how much it is. One chimney per hour emits how much? This is actual data. from one power plant. One chimney emits how much? Can you tell me how much ton is that? 3000 ton, close to 3000 ton per hour. 3000 ton per hour, right? Everybody is with me? Assuming this is about 20% of carbon dioxide, easy for calculation. How much it is that? 600 ton per hour multiplied by 24. How much? Tell me how much ton per hour, per day? Huh? More than whatever it is, 1800. One chimney is emitting. They have 3 chimney operational. How many power plants we have in India? Find out. How many power plants are there in the world? And this is happening continuously 24 hours, 360 days a year. Right? CO2 molecular weight is 44. C is 12, oxygen is 16, 20, 40, 44. Total is 44. Air molecular weight is 29. What is heavier? CO2 is heavier. So it will form a blanket. The concentration of CO2 is relatively more near the Earth's surface rather than above. And therefore, even though the concentration is less, it will form a blanket of CO2, which is really not really worried about as far as life is concerned. But as far as capture of this radiation is concerned, they get captured and they increase the local temperature. And this is augmented by other factors as well. You have concrete jungle, etc., so on and so forth. So there are local heat spots available. So it's a one-to-one equation. That also helps to increase the temperature. So the question is that when they looked at the temperature that goes off for the flue gas, it is about 150 degrees centigrade. I asked them, why don't you cool it down? I said, if I cool it down, the sulfur dioxide will deposit in my chimney and it will corrode. So they do not want to do that. So they are releasing the heat into the atmosphere at the cost of avoiding sulfur accumulating in their chimneys. Of course, CO2 is going out there. Alright. So this is a situation. Now when I say the carbon dioxide property that I have discussed, the carbon dioxide is not a single molecule available in the atmosphere or even in the flue gas. It is available along with different other components of gaseous state. So therefore the properties will change. Properties like density, viscosity and so on and so forth. So you require equation of state models. You must have studied that, equation of state models like Pink-Robinson, SRK, so Reddit-Kong and so on and so forth. So to use those equation of state models to understand the properties of flue gas, you want to transfer and design your operations to separate carbon dioxide from the flue gas. Everybody is with me, right? Now, what are these important aspects of flue gas generation in the power plant? Now, as I said, energy is important, so we cannot stop going away right now from the coal-fired power plant. So typically we have power plant that has to be connected with CO2 capture systems, like is shown here schematically. You can have a CO2 scrubber, SO2 scrubber, as I said, that you have to separate out. Ensure that you require different types of material because it is not easy to handle SO2, sulfur dioxide. You have a flue gas that goes into the absorber where you can have a different systems of like amine systems. You can separate CO2, capture that. You can have a stripper unit and then you can separate the pure CO2 and then the CO2 can go into the sequestration or transportation. You are getting my point? So this is a typical schematic of how the combustion and associated CO2 capture process looks like. Let me come, right? Now there are 3 major types of combustion. Either you can do a pre-combustion capture of CO2, you can do a post-combustion capture of CO2, right? You can capture carbon dioxide before you generate it into the atmosphere. So you can have a pre-combustion process where a fuel can convert into gaseous mixture of hydrogen and carbon dioxide. Partially you oxidize that. So you oxidize coal in oxygen and air and then you generate a synthetic gas, syngas. The synthetic gas can further be converted into richly hydrogen and carbon dioxide. right. So the advantage of that is that you are actually capturing carbon dioxide which has reasonably higher concentration of CO2, so that it becomes easy to capture CO2. As I said, when you have less amount of CO2, it becomes very challenging to capture. When you have heavier or more amount of CO2, then you can have a better chance of capturing it. And then hydrogen can go into the power generation, electricity generation, and then you can actually capture that CO2 and store that, right. So here the CO2 in the mixture can range from 15 to 20%. This requires integrated gasification combined cycle power plant. These are less available. People are reluctant to do that unless, because this doesn't really add any value to them technically, economically. So unless they get some money, they do that, or they don't do that, right. So this is a money game primarily. You know what it really makes them economical, that's the question. Now the other method is post combustion capture. So these are limitations, as I said, I didn't do that. So this, they have a high efficiency and relatively easier carbon removal from fossil fuel. The advantage is that the hydrogen that is reached into the stream can convert into the electricity efficiently. However, the overall capital cost of the base gasification process exceeds the conventional pulverized coal fire power plant, and that's discouraging their adaptability at more. The cost of absorption process required to capture CO2 generated by ICGS power plant can range up to $60 per ton, which is still not very attractive to the companies, right. The other disadvantage of pre-combustion capture that includes limited IGCC plant, decay issue with utilizing hydrogen rich fuel, and heat transfer challenges. So some of these challenges are there. Again, as I said, like hydrogen handling, hydrogen is again a very challenging task, right. So this again has a safety issues and so on and so forth, right. So this is still at a stage where more research has to be done. Then we have post combustion capture, which is right now something that people are looking at attractively, because you combustion it and then capture CO2, and technologies are available ready made, because you can use conventional technologies to capture carbon dioxide. The challenge is that here the CO2 is very less into the stream. It can be less than 20%, 7 to 14% sometimes, and 4% in gas power plant. So this is very challenging to compress that, but it is reasonably easy, as compared to pre-combustion capture. So this is what post-combustion capture schematic looks like, right. So you generate a fuel, burn fuel, you have exhaust gas that goes into it, you have electricity, and then you capture carbon dioxide and store that or transport it for subsequent processing. Something that is very attractive is oxy-fuel combustion capture. Now oxy-fuel combustion capture is something that is more promising technology that people are looking at it. Oxy-fuel combustion uses a pure oxygen stream. So I am not really going to use air as a source to burn a fuel. I will use a reasonably pure oxygen stream to burn the fuel, so that I generate more amount of CO2 which is rich in concentration. It's become easy for me to separate or capture that CO2, or it is possible that I may not necessarily require to capture that CO2, because even I can have a 70-50% or more than 50% of CO2, I can use that directly into the underground storage. I can transfer that right directly below the storage. I do not have to, so I can address the capture part of it costly partly, but I can use pure CO2, a pure oxygen stream to burn that. So this is a schematic that shows that you have a air separation unit where you generate more oxygen. So COVID time oxygenators were used, right? You know that, right? So you get oxygen from air by separating it a small unit, right? So similar kind of stuff here. You can separate oxygen from the air, use the more pure oxygen into the boiler, and because you have oxygen mainly, there will be a complete combustion expected, and so you have a more CO2 that goes into the exhaust gas, which is become easy to capture, and then you transport that storage site, and of course you get electricity out of it, right. So this is a schematic of what I have talked about, right. You can also have a sulfur that may come out, so you can capture the sulfur. So reasonably it is easy to capture CO2 from this stream, right. Still, this has been used primarily in steel making and metal cutting industry, but in recent time it also has an advantage that it has a high flame temperature, because you are using more better quality oxygen, you can have a better flame temperature also. So the efficiency of the power plant may also increase. There also may be challenges with the heat losses, because you have more flame temperature, so heat losses has to be curtailed, right? That's what is, we have oxy-fuel carbon capture. So now you have this something that's different from that. It's still challenging, I am saying that. So we have to look at the cost benefit, So all the decisions will depend upon the cost factor. Now what I am trying to tell is that this is a promising way. As a technologist or as a scientist, I feel that this is a very attractive proposition for me. Now, of course, cost, how we can come down, can have a better technology that I can separate oxygen from the air, that we have to look at it, right? So this is a cost game ultimately. Anything that we have to put a plant, cost will play a role. Yeah, of course. Yeah. So this is the overall scenarios. We have post combustion, we have pre combustion, we have oxy fuel, and there are certain industrial processes where you generate oxygen, you have a separation unit, CO2 separation unit, and then you compress and dehydrate that. Now this is a capture part of it, right? So you whole lot of technologies that goes in. As a chemical engineer, we have absorption, adsorption, etc. All these concept that goes into that to separate out CO2 from flue gases, right? More focused on this, right? So this is a CO2 capture traditionally done in oil and gas industry. As I said, natural gas reservoir often produce carbon dioxide. So to separate that, amines were used often in oil and gas industry, and mainly in other industries, very widely accepted solvents, right? So this is a CO2 separation and C2 plus recovery plant in Middle East, right? So they separate out sour gas, I mean the CO2 and H2S. You can also have a dehydration unit where you separate out water, and then you have a product gas, and you can actually have CO2 and H2S that might go into the atmosphere. They may not really worry about it, because that is not enough CO2 that can be transported, so they may release into the atmosphere, or they may sequester it into the subsurface reservoir, right? So these are something that is being practiced in the industry. It's not something that is. So the major solvents based system, and in next couple of weeks you will hear in different technologies, people may talk about adsorption, etc. I will just briefly tell you that amines still being utilized widely, a solvent system, because they have a better efficiency to capture carbon dioxide. It can go up to beyond 80% in certain cases. Your set of amines, you can have a monoethanol amine, we have a dimethanol amine, methyl diethanol amine, MDA, and they have a concentration of lean solutions, and this is a typical guideline when it can be used, So depending upon the case to case basis, their selection will decide, which will give me a better solution, right? So conventional equations that tells that you can actually convert CO2, capture CO2 in amine carbamates. You can also capture H2S gas from say natural gas systems. You can have amine sulfides, and then you have typical schematic where you have amine absorber, you can have a stripper, and that right, absorption takes place at relatively 40 degrees centigrade. You strip it at say about 100 or more than 100 degrees centigrade, so you separate the carbon dioxide from this stripper and then separate that and take it away, right? So design aspects can be looked at it, how much size of absorption and desorption columns are required based on amount of flue gas that you can handle. A simple chemical engineering principle that goes in, equilibrium constant and equilibrium ratios, and number of plates that may required, or packing height that may required, right? So all those simple calculations can be possible over here, right? Now there are power plants available, there are CO2 capture plants available. It's not that this is started recently, but very less efforts were done. In 2009, this is in Alabama, power company plant in Berry, which is one of the largest that time, based on coal fire power plant. So here CO2 was captured using amine solvents technology, right? And this is transported to a geological storage site, right? About 114 kiloton of CO2 was captured, transported, stored, and monitored through the pilot project. So this is done in 2019. There were efforts made in 15 years before, right? Now it has been accelerated. This is something that Norway's Sleipner project, very famous, and Japan's Tamakomi project. You can see that Norway has started looking at CO2 capture into offshore subsea sediments or saline formations more than 25 years, right? So it's there. Sleipner project separates CO2 from natural gas produced at offshore platform, and CO2 is then injected and stored into the adjacent offshore formation beneath the sea floor. And in Japan project, this is a demonstrated project by Japan Carbon Capture Sequestration Company, which was commissioned and recommissioned in 2018 and 2012 and 2020, and they have shown that CO2 can be captured and transported for subsurface geological operations. So there have been efforts made. I will also show you in one of the next class that there are additional efforts which have been made at the pilot scale. Now we are not behind, but we are doing a small step, being an academic institute. So as I said, like SAPEcorp, they came us with that, and they said that okay, we have this chimney and we want to capture the CO2, carbon dioxide. So this is some efforts that we have done, for power plant, and we then started looking at it. And Yogendra is sitting next to me, he is my PhD scholar. He worked on amine solvent and improved its efficiency by a certain magnitude. And then we filed a patent and we got this patent approved very recently in 6 months. This is Indian patent, we got it approved, and now a pilot plant has been ready for installation. So this pilot plant has been delivered in the field in power plant in SAPEcorp, not, this is about 4 hours journey from here. So this pilot plant has been developed based on this patent, and we are trying to do some studies over there so that we can try to see if the CO2 can be captured efficiently based on the system. Amines, why we have selected, because it is a very proven technology, it's there. So I can improve that technology further by one step magnitude, and then I can use that for my application. So this is being done, we will have results hopefully in 1 month or 2 months time to see, and once we are done with this, we have to just multiply that. I do not have to really reinvent the wheel, I already invented the wheel, I have to just re-multiply it. So we are just waiting for the results outcome, possibly we will see that. Now transportation and transport process is a very important factor here. It's not something that I capture it and forget about it, right? I have to store it. I have to store it in a storage tank, then I have to liquefy it. I have to transport that by tankers. I can transport that by ships and pipelines to the storage site or even in the industrial application, right? So CO2 is not something a very easy molecule to handle. Even though it is not flammable, it is highly corrosive to the environment. Any system of metal that you expose to the carbon dioxide, which is rich in concentration, will corrode over a period of time. Less concentration, I do not have to worry, but if I want to handle a pure carbon dioxide, it's not an easy task. It's highly corrosive system. Even oil and gas industry is putting lot of money to handle or to develop materials which can address handling of carbon dioxide at certain temperature. CO2 become more corrosive at higher temperature and pressure conditions. So this is again very challenging task, right? So if you look at this transport process, it is required because you have to transfer that, to sequestration site for NS oil recovery, for coal bed methane recovery, for offshore or onshore or industrial requirement, right? So this is a total schematic, which shows that you have to store and load, and then you have to ship and then sink, right? Pipeline transportation or transportation by shipping carriers, So these are something that we have to worry about it, right? So there are various methods. I can do that into the ocean, deep sea CO2 storage site. You can do this via injection platforms like this. So I can use existing oil and gas platforms offshore or onshore to do the sequestration. So I do not really have to worry about too much of additional capital investment. Of course, in certain cases I may require that, but I can use that, However, you have to worry certain aspects of corrosion, hadite formation and fracture that may result in metals. So it is not, again, if I want to transfer that at low temperature, high pressure, then metal may not be able to sustain at those conditions, right? So I will tell that, so you can see this kind of corrosion. So types of corrosion that can happen due to CO2 and other acid gases. So everybody knows that CO2, when it comes with water, can form acids. Yeah, pure CO2, but getting a pure CO2 is very challenging. As I said that 100% pure CO2, that's what I am telling you. So even small moisture that goes in, dehydration, storing it. As far as pure CO2 is concerned, you do not have to worry about it. But if it is not completely pure, then it may provide certain amount of corrosions into the systems. So, but are you able to generate a pure CO2? What is the percentage? Agreed. But in case if you do not have that much of pure CO2, process, yeah, of course. Agreed. So, yeah. So, my objective here is to tell that why the pure CO2 is very necessary. If you do not have a pure CO2, if you have water vapor, yeah, agreed. But that's what I'm telling you, because when you do not have a pure CO2 available, here pure means maybe without water vapor, without any additional gas stream that may be hazardous to the metal, then you do not have to worry about it. But if you have moistures along with it, if you do not take a care of it, that if there are certain kind of contamination happens during the transportation, pipeline for example, there is a leak, there is walls available, etc. It's possible that something may leak in. So if you do not have that kind of system where it is leak proof, the other challenge is that if your temperatures are lower, then you may have different types of issues. You may have a stress induced corrosions, you may have intergranular corrosion, you have cervic corrosion, selective leaching, you have pitting, etc. So there are different types of corrosion that may affect the material strength over a period of time. For example, liquefied natural gas, that also doesn't have water vapor, but they say that at low temperature the normal steel cannot sustain, because that may make it more brittle. So if you are transporting CO2 at much lower temperature, certainly sometimes people say that okay, I am going to transport at minus 30, that will reduce my pressure for the container. Either you increase the pressure or you reduce the temperature, that will give an advantage to transport, right, material. So at certain conditions it is possible that you may have different types of issues with the metal. So all these aspects has to be considered. If you have water vapor that goes in, then you have a certain types of corrosion that may get induced into the metal. So you should have a precautionary measures that has to be taken place when you are designing a transportation processes, right. So the other aspects is a ship, right. So that's what. So CO2 carriers, typically has a capacity of about 1000 meter cube, and they can transport about minus 30 degrees centigrade and about 50 to 20 bar pressure. So low temperature, when you go beyond that, then you have a brittleness that may affect the metal strength over a period of time. The ship tankers can be categorized in pressurized, semi-pressurized and fully refrigerated, and depending upon the temperature condition and pressure condition, these are being categorized. This is a schematic design of how the CO2 tankers may look like. You have a top view, you have a side view, and these are being very well contained in ships, and these like LNG tankers, a similar kind of technology can be adopted to generate such kind of capacities, and we have to see that how this CO2 can be transported, stored by pipelines and through your ships, etc. right. So a whole lot of things that may require to understand this schematic. Now once you do that, you can inject that in the subsea sediments through subsea injection well. You can have risers that again oil and gas industry uses that, so you can exploit that for this injection, or you can do that using unloading arm and existing injection platforms likewise. Schematically it is shown here, right. So all these possibilities are there. Now the cost plays an important role. So this is not a data, this is a data from IPCC, I have just taken it for that. So this is a cost breakup when you talk about ships and overall process of liquefaction. So you can see that the ship accounts for about 30% of cost, and liquefaction accounts about 42% of cost, and then your unloading 16% and storage 9% and loading is about something like that. So this is I have taken it from IPCC data. So I do not know how did they come out. Then you can also look at the cost US dollar per ton of CO2 for 250 kilometer range, and it shows that onshore provides a lower cost because it is easy to transfer. But as you increase the mass flow rate of CO2 per year, then offshore transportation is also something that can be attractive. Not cheaper than onshore of course, but it shows that I should have a more transport of CO2. I should not generate offshore project if I want to just transport 5 metric ton of CO2 per year. That's not something that I should look at it. I should plan it for significant CO2 transportation capacities, right. And this is shows how the ship cost. So it shows this transportation cost US dollar per ton of CO2 over a distance, right. So less than 1000 kilometer, the ship shows a higher cost, and offshore pipeline continues to increase dramatically. Onshore pipeline also increases as a distance increases, but ship cost reasonably comes down below the onshore and offshore conditions, right. So it shows that transportation of CO2 by ships for longer distance may be an attractive proposition, right, based on this, right. So cost plays an important role. As I said, that we are doing something that requires a penalty in terms of cost, and we have to see that what is best that we can do to make sure that we do this process overall conveniently. Now, other aspects that I think madam will certainly discuss in detail, that CO2 injection onshore can also be done to recover more oil from the reservoir. So thereby you can actually generate oil and you can also sequester CO2. So there are different phenomena that govern CO2 sequestration. Mineralization is something that takes long time, but you have capture by poor network of CO2 in a short time scale, etc., and over a period of time it get mineralized, right. So there is a lifespan of CO2. What happens to the CO2? What is the fate of CO2 that goes into the geological formation? So there are certain studies available which indicates that CO2 storage for long term time span can be more stable in onshore as well as offshore condition, right. So this gives certain idea about some idea about CO2 capture, and we will discuss some more details about that. I think we should stop here for today.